So far we have been covering static games where the underlying assumption is that the agents who are involved in these games make simultaneous and once and for all decisions and then observe the payoff. So the limitation of that scenario is that the agents are interacting only once. But this is not true for a lot of the real-world scenarios where we're actually interested in the sequential interaction between the agents. And there's a need, therefore, to extend static games to games that allow sequential interactions. And today we're going to look at a very natural extension, namely extensive form games, that goes from static games to the games in a dynamic setting. Let's consider, first of all, this example. This is what we call a battle of the sexes game. A couple would like to choose an evening venue, but they have different tastes. For example, one of them prefers opera and the other person prefers football. Right? And then we can see that, of course, both of the agents, both of the people would like to go to a venue together. So the payoff for them disagreeing on the different venues will be 0 to everyone. So this is not serving either of the persons. However, they do have different preferences. For example, one of them would like to go to an opera and the other would like to go to a football. So if they both go to an opera, then player 1 would get a payoff of 2 and player 2 will only get 1. Similarly, if they both go to a football, then player 1 will get a payoff of 1 and player 2 will get 2. So, of course, there are two Nash equilibrium, OO and FF, if we treat it as a static game. But in reality, let's consider the situation. Well, they're not actually making decisions at the same time. So player 1 may finish work earlier than player 2, and thus she can make the decision first. And of course, she can just make a decision by herself and arrive at the venue, and then once she's at the venue, she would message the second player with the location saying, okay, I'm here, will you join me or not? So player 2, after seeing the message, would then make a decision on where to go. So now this time player 2 will have already some knowledge about the decision of player 1. As a result, she will respond to it, right, instead of making the decision simultaneously as player 1. So in this case, what do you think the outcome will be, right? So the outcome will not just be a random choice between OO and FF, because player 1 has already made her mind about where to go, right? So this is a scenario that's not captured, at least on paper, by the normal form game that I introduced. So we have to extend the model, right? In static normal form games, the player make decisions simultaneously, so each player conjectures a belief and plays a best response to the belief about the opponent. If the player make decisions sequentially, then the player's belief changes as the game unfolds. Once the player get to know about the decision of a player, then the belief changes. So such a game can be best described by a sort of a decision tree, or in this case we call it a game tree. We know that, for example, player 1 makes the first decision on either to go to the opera or to football. So she would just make a decision. So you can see that we can make a tree where the root belongs to player 1, and there are 2 branches that go down to 2 children of the root. One is the outcome when she chooses the opera, and the other is the outcome when she chooses football. And of course, starting from both of these children is now the decision of player 2. So the nodes would now belong to player 2 for him to make a decision on whether to go to the opera or the football. So you can see that we have the branches from each of the level 1 nodes to level 2. And then, so assuming that that's the end of the interaction, so at the end we have 4 possible outcomes. There's a OO, there's a OF, there's a FO, there's a FF. I'm using capital letters to denote the decision of the first player and small case letters to denote the decision of the second player. And then for each of the outcome which correspond to a leaf of the tree is labeled by a corresponding payoff. So you can see that it's a bit different from the matrix forms of game representation that we've seen for normal form games. There are a lot of similar scenarios that can be appropriately modeled as a tree. For example, strategic bargaining. When a player makes an offer, the other player either accepts the offer or reject it or plays a counter offer. And this is repeated for a number of rounds, and you can see that that is a sequential forms of decision making, and it can be modeled as a tree. On another scenario, it could be, for example, there's a market when one of the company is occupying the entire market, but then there's a new company who sees the opportunity to enter the market. Then player two, well, the first player would then need to decide on how to compete, either aggressively or ceding some of the market shares. That will also be a sort of a sequential interaction scenario. A Stackelberg competition, which has been extensively studied in game theory. That's when we have a market, when there is a market leader and there are a bunch of market followers. And also chess-like game. These are especially relevant for AI research when the players alternate in making moves. So this is definitely very, very relevant and very, very important. So how can we formally describe the tree? So I can define the game tree as a rooted tree where the leaves are called terminals and the other nodes are called non-terminals, but every non-terminal node is associated with one of the players. So when this non-terminal node is associated with that player, it means that that player has the right to move at that node. So you can think of these nodes as basically states of the game. So every non-terminal node is associated with one or several actions in the action set. Right, so each of these actions is used as a label on an edge to a child, and for each player I, a payoff function associated every terminals and leaves a real value payoff. Right, so that's the game tree, and by a perfect information extensive form game, we just meant to have a number of players and a set of actions for the players, and then a game tree. Right, and essentially you can think of the players playing according to this tree. Right, so that is our model, and once we define a game model, we need to define strategies. A pure strategy for a player is basically a function that assigns actions to each non-terminal node that belong to this player. Right, so this basically says if the game has entered that state, which is this player's turn to move, what would this player do? Right, that's specified by this strategy. So it's sort of like a rule book, and the player can then, with this strategy, play this game. And whenever it observes that the game is in a certain state, and if it belongs to that player, then this player makes a move according to the rule book. Strategy profile, of course, will be a strategy for every player in this game. So with the strategy profile, then we can see how the game can be played. Right, so basically determine path in the game tree from the root to the leaf, and not just from the root to the leaf, but essentially from every non-terminal node in the tree, there is going to be a path to some of the leaves. Right, so consider that previous game. Of course, it's a very simple game with 2 levels, and we have the following strategy. The strategy could be, remember when we define the strategy, we need to specify the action on every non-terminal node. Right, for player 1, for example, there's only one node that belongs to player 1, that's the root, and it could be either big O or big F. So let's say player 1 just plays big O. And player 2 has 2 possible nodes because there are 2 nodes which belong to player 2 at level 1. So it could be, for example, when player 1 chooses capital O, then player 2 chooses small o. And when player 1 chooses capital F, then player 2 chooses small case f. Right? That will be a description of a strategy profile in this extensive form game. Right. And for simplicity, we can ignore the sort of the mapping from the node to the action. So we can just order the players' nodes on the tree in some fixed order, and then we just write down the actions in the sequence. For example, for S1, we just write capital O. So this represents that at this node, which belongs to player 1, the player would choose O. And for player 2, we can just write it as small case O and F. This is showing that in one of the states, he would choose small case O, and in another state, he would choose small case F. Right? Just for ease of notation. So let's think of this game. This will be an example where we have this game tree, and we have two players. You can see that on top of each node, each non-terminal node, we have a label of either 1 or 2, indicating which player this node belongs to. And then we have a number of actions for each player. So for 1, there are 2 nodes that belongs to 1, and the actions for the first node is A and B, and the actions for the second node is G and H. For player 2, there are 2 nodes also. One of the nodes has actions C and D, and one of the other nodes has actions E and F. And you can see that on top of every terminal, on top of every leaf, there are 2 values indicating the payoff to player 1 and 2. Right? So we can write down the strategy sets for the players. For player 1, there are in fact 4 ways that the player can play. So for example, AG is one of the strategies. This says that in the first node he will play A, and in the second node he will play G. Right? AH would be, when the first node he will play A, and in the second node he will play H. For the second player, of course, there are also 4 combinations of possible strategies that the second player can play. So that's the set of strategies for the player. So this suggests a way to convert that extensive form game to a normal form game, right? Because if you think about the situation where player 1, instead of having these choices, but instead if you think about it, there are only finally many possible strategies. Each strategy is in the form of a function, but there are 4 such functions. For player 2 also, there are 4 such functions. So we can actually draw a matrix, which is a 4x4 matrix. On the rows, it indicates the possible strategies for player 1. At the column, it indicates the possible strategies for player 2, and then at each entry is just the corresponding payoff to the players. And you can see that in this way we convert this extensive form game to a corresponding normal form game. And in fact, these 2 games are equivalent. Right? So for every perfect information extensive form game, there exists a normal form game that has the same strategy space and payoff, and therefore these 2 games are equivalent, and we can just analyze the normal form game in order to analyze the situation of the extensive form game. Right? Of course, if you look at the complexity of this transformation, it may lead to an exponential blow-up, because if you have, for example, several such nodes with 2 options for the player, then you have exponentially many possible strategies. So the table can get very, very large when the tree becomes large. However, the other direction does not hold, right? So if you look at any normal form game, for example, if you take the matching pennies game or the static battle of the sex game, where the players are making decisions without knowing the opponent's decision, that cannot be captured by a perfect information extensive form game. So we cannot draw a game tree where the players do simultaneous moves, right? So that's the limitation. It seems like now, right up to this point, extensive form game is a weaker form of normal form game, and everything that we can do for normal form game can be transferred directly to extensive form game. So what's new here, right? That's the question. Of course, the previous limitation is actually not a limitation if we are able to relax the definition of extensive form game a little bit. For example, if we consider a static normal form game, right? So we have this battle of the sex game where we have two options for each player, and suppose they make simultaneous move without knowing the other person's moves. Can this normal form game be used to describe situations of non-simultaneous moves? Right? It could be, well, because when we define normal form game, it said that they're making simultaneous moves. But I also said that the simultaneous move does not mean that they have to make the decision at the same time. It could be that one of the players is making a decision before another player, as long as the first player is not aware of the decision made by the second player. So the key thing with the simultaneous requirement is not on how they make decision at the same time, but really about knowledge. So you're making a decision, but you're not revealing that decision to the other player. In this case, you can think of the two players as being simultaneously moving together. Right? So all we need is that one of the players does not know the decision of the other player. So this means that it's not able to distinguish the nodes capital O and capital F after player 1 made the move. Right? So now this gives us some sort of idea of how we can transform that normal form game to a corresponding tree-like extensive form game. And this can be represented on this tree by somehow connecting the two nodes which correspond to the different decisions of player 1. Right. So recall that in a perfect information extensive form game, starting from the node that belongs to player 1, there are two branches, one going left and one going right. This corresponds to the two decisions, the possible decision of player 1. And then from each of them, player 2 would then make decisions assuming that they know which node player 2 is on. Right. In an imperfect information case, player 2, although player 2 knows that player 1 had made the decision, player 2 is not able to distinguish the nodes O and F. Right? So in this case, player 2 have to make a decision independent on the action of player 1. And this will correspond to exactly the same situation as in a normal form game where the two players make simultaneous independent actions. Right? So all we need as an extra thing between this type of extensive form game and this type of extensive form game is the possibility to collect nodes together and say that this is a set of nodes where the player cannot distinguish. For example, in this case, these two nodes are collected in a set, and any node within the set cannot be distinguished from each other. Right? And we call this set an information set. Right, so this and on this tree, I draw a circle. Sometimes not a circle. I draw a dashed line connecting nodes. This indicates that these two nodes belong to the same information set, and if you cannot distinguish these two nodes. Right. So that leads to the idea of perfect information extensive form game. Right. Formally speaking, an imperfect information extensive form game is a tuple with a set of players, a set of actions, and also the game tree T. But not only that, we have an information set relation, right? So instead of representing as information sets, I'm basically drawing up a number of equivalence relations, one for each player. And for every player, I have an equivalence relation, and this equivalence relation denotes that the player cannot distinguish two nodes, right? So I have this capital letter I, which consists of a tuple of equivalence relations. Each equivalence relation I belongs to a single player I, and this is a relation that's defined on all of the non-terminal nodes that belongs to player I. And HII equivalence class is what we call an information set. If two nodes belong to the same information set, then they are assigned to the same player and have the same available action. So that's the requirement, right? And you can see that this is a generalization of perfect information game, because in a perfect information game, we just assume that these equivalence relations are identity relations. So this means that every equivalence class contains a unique node in the tree, right? Then how do we play this game? Right? We need to define strategies. The strategy can be just a generalized version of pure strategies for extensive form, for perfect information extensive form games, except that it's no longer a function that maps from nodes to actions, but rather from information sets to actions. Because remember, in this imperfect information situation, the players cannot distinguish nodes within the same information set, right? And therefore, whenever we fall into an information set, we assume that the player can only make one set of of choices. And pure strategy profile, of course, would be just a tuple of pure strategies of the player. So now consider the previous game. Now this time it would be an imperfect extensive form game. We have two information sets. One belongs to player one. So player one, of course, has only one node, and therefore that node itself forms the information set. Player two has two nodes, but in this context, we assume that these two nodes are belonging to the same information set, and therefore only one option, one action is decided for all of these nodes. And we can design a strategy profile, say, for player one, he would just choose to go to the left. So pick the capital O as the action. For player two, instead of identifying an action for every node, it's identifying an action for this information set, which is just small case f. Right? We can simply write that strategy as capital O for player one and small case f for player two. Right? You can see that now this game will be the same in a conceptual level as the normal form game, because the normal form game just assumes that the two players act independent of each other, and the same here, the players make actions independent of each other's actions. It feels like everything that we want to ask for about extensive form game can be answered through analysis of normal form game. Indeed, this is the case for many applications, but in some cases we see that we need a different type of equilibrium. But before we get to that, let me introduce some more complex formal strategy. So remember, when we're dealing with games, we have pure strategy, we have mixed strategy. So pure strategy would be just a functions that assigns information sets to actions. Mixed strategy, just like in the normal form case, it will be a probability distribution that's defined on the set of all the pure strategies. So this will be a distribution on these functions. However, in real life, we typically are making decisions as we play the game. So as we acquire new information about the game, about the state of the current environment, we make a certain randomized decisions. So that would be a strategy that's not pure because of the randomized moves, but it's also not exactly a mixed strategy because we're not defining the probability distribution over all of the strategies beforehand. We are deciding on the probability of taking certain actions as we move to different nodes in the game tree. And this type of strategy is called a behavioral strategy. So this means it's abstractly as defined as a function that assigns probability to all the actions from a single individual information set. So for every information set, we look at all of the collection of actions that we can choose, and we assign a probability distribution on those actions. You can see that this is very different from the mixed strategy. As an example, if we have this game, you can see that one of the potential mixed strategy for player 1 would be, for example, he is mixing the strategy AG with the strategy BH. Right? So AG is when player 1 chooses A at the first node and chooses G at the second node. And BH is this decision on the first node and H decision on the second node. And he's mixing 40% of the first strategy and 60% of the second strategy. So this means that when he decides on this mixed strategies, it's already looking at all of the possible moves at all of the possible information sets. However, in a behavioral strategy, it will be slightly different because it could be saying that when he's at the first node, he's mixing A with a certain amount of B. So he's mixing 0.5% of 0.5 of A with 0.5 of B. And then at the second node, he's mixing 0.3 of G with 0.7 of H. Right. So that will correspond to strategy at a more of a behavioral level when the game unfolds and when the player reaches a certain node, the sort of mixture of strategies that the player adopt. Right. That's what we call behavioral strategies. Right. When we define imperfect information games, there are certain quite difficult cases. For example, we have this situation when both of these two nodes belong to player 1. So this corresponds to an action of player 1 deciding on whether to go left or right. And when he goes left, the game stays at a node which also belongs to player 1, and this also corresponds to whether he will choose to go left or right. And to capture the imperfect information, we use a dashed line. So this dashed line plays the same role as the circle in the previous diagrams. So this means that this node and this node belong to the same information set. Right? What do I mean by this? So consider the situation where we have a agent who is making moves. Whenever it makes a right-hand side move, it knows that it has made this move. But whenever it is making a left-hand side move, it forgets that he has ever done this, make this decision. Right? So this is like a driver driving on the highway. If it decides to leave the highway at an exit, he knows that he has left the highway. But if he just drives on to the highway, when he reaches the next exit, he has forgotten that he has made this decision. Right? So that's a sort of like a weird situation, and this is called a imperfect recall. Right? This is a situation when player 1 forgets about the decision that they have made in a non-terminal. And games with imperfect recall are somehow special types of game that are difficult to analyze. And there's a rich literature on such games which is beyond the scope of this course. So I'll just give you the definition of that, but I won't go into the detail of the analysis. Instead, we just always assume that we have perfect recall games. So a player I has perfect recall in an imperfect information game if they never forget information that the previous low. No, right? So the previous situation would not occur. This is our assumption. This means, in a more formal definition, for any two nodes x, x prime in the same information set, these two nodes, so these are the nodes x and x prime which cannot be distinguished by a player I, right? So they must lie on the same level of the tree. And also, for any pair of nodes y, y prime that lie on the path from the root to x and then to x prime respectively. So imagine a picture where we have the root going to x, right? Because it's a tree, there's a unique path, and suppose y is in this path, and then from the root to x prime, there's another path. and then y prime is on that path. For any such nodes y and y prime that are on the same level of the tree, and suppose these two nodes both belong to player I, right, the same player as the holder of x and x prime, then y and y prime must also be in the same information set, right? So intuitively, this just says that player I will never forget the decision that it has made, right? So basically, in this situation, things becomes much easier. So consider two strategies equivalent if they induce the same probability on outcomes for any strategic profile of the remaining player. Then we have this Kuhn's theorem in the 1950s that says in the game with perfect recall, we don't need to consider mixed strategies. We just need to focus on behavioral strategies whenever we have uncertainties in players' actions, right? So any behavior strategy can be replaced by equivalent mixed strategy and vice versa. Right. So this shows that it's okay to just focus on mixed strategies. Next, we want to investigate solution concept of such games. We want to be able to make prediction on the outcome of such extensive form games. But like what I said, any extensive form game has a corresponding normal form representation. And therefore, any solution concept that holds for the normal form game also can be extended to extensive form games. So we can, of course, define a pure strategy Nash equilibrium in an extensive form game to say that strategy profile satisfies the condition if for all the players that player is playing a strategy that is the best response to the opponent's strategy. Right, that's exactly the same definition as Nash equilibrium in earlier lectures. Any perfect information game in extensive form game has a pure strategy Nash equilibrium. Because in a perfect information game, you can see that once a player takes a turn to act, and everybody can see every move so far in the history of the play, and this means that there's essentially no reason to randomize. You know what the opponent has done. You're just playing it according to your best interest, right? So that's an intuition here. So of course, perfect information game is just a very special subtype of extensive form games. And typically, when we talk about extensive form games, we would be looking at imperfect information games. Let's look at this example where we have the battle of the sexes. And this is the sequential perfect battle of the sexes. Right? What will be the Nash equilibrium? Right? How can we analyze this? We just need to write down all of the players' strategies in a matrix in the same way as we do for normal form games. Once we have the game matrix, payoff matrix, we can use the same method to identify the Nash equilibrium. In this case, we have quite a few Nash equilibria. We have the OO, this case when first player chooses to go left, and then the second player chooses to go left. Notice that when we specify the game outcome, of course, this will be just a single pass in the game tree, but when we specify the strategy, we definitely need to specify the actions in those other nodes, even though they are not reached, right? Because when the player decides to play the strategy, he's not just deciding on what action it would take when we're playing in this main branch, but also the action for all of the nodes that belong to this player, right? So even though the game has never reached this node, in this strategy profile, the second player need to determine beforehand that he's going to play small case O at this node, right? Similarly, another Nash equilibrium is big O and OF, so this would be big O, and player 2 would be just small case O, and then this place is F, right? And another possible Nash equilibrium is FF, so it would be F and F and F, right? Notice also that these big O OF and big O OO have the same outcome to the game. So the main branch of the game, which is the branch that really the two players went through if they played the game, they're the same. So it looks like these two strategy profiles are very, very similar, but they are quite different in terms of the intention of the player 2 in our unreachable information. So, for example, this other Nash equilibrium will have capital F and FF, then player 2 actually act irrationally at node capital O. Right? At this node, player 2 is actually not very rational, because player 2 is saying, well, I want to go to F, so if you go to O, I will still go to F, and then we both will get 0 and 0. So what do you want to do, right? And if that's player 2's strategy, then player 1 will play capital F, because player 1 will want to at least receive something as a payoff. Right? So you can see that essentially player 2 is using this strategy to push player 1 to adopt the strategy that he wants. So this can be illustrated by another example when we have the Cuban nuclear crisis. Of course, it's a very simplified representation of the real scenario, where we have Russia deciding to arm Cuba or retreat, and the U.S. deciding either to respond by starting a nuclear war or fold. Right? So we have these two options, and for any of the people who are interested in Cold War history, you can look up the video on what actually has happened in real life. But essentially, the situation becomes a crisis because of the fact that one of the countries is using a threat to push the other player to adopt a strategy. And that's a dangerous move, because this means that it's possible in a Nash equilibrium for a player to not adopting a rational decision. Right? So one of the Nash equilibrium of this game is that for Russia to choose to retreat, and for the US to choose to nuke the world. And that's one of the Nash equilibrium of this game. And when this happens, this is when the US is threatening to destroy the world in order to push Russia to retreat. But that's a dangerous thing, because as in any case, the society, as in any case, there's a degree of uncertainty. And random events is likely to happen. And if the U.S. is determined to follow this strategy, there's a real chance that the world gets destroyed by a nuclear war. And apparently the problem is when this player is not playing at the best interest, at the best response, although that's in a Nash equilibrium overall, right? So that is posing some sort of need to consider maybe a tighter or a stronger form of equilibrium. Not only we require that the agents to act rationally at the overall game, because the game is a sequential and the game is developing as the agents are making their moves, we would not just want the player to be rational up front, but we want the player to be rational along every step of the dynamics of the game, right? So in the Nash equilibrium, of course, the player's action do not take into account the dynamics. Even though players respond optimally giving prior belief, they may not act optimally as the game unfolds, as is illustrated by the previous cases. So for a given player, and given the opponent's strategy, a strategy for this player I is what we call sequentially rational. If player I is playing a best response to the opponent's strategy in every information set, you can see that this is a stronger form of best response, because in the best response assumption, the player only need to be playing his best interest at the root of the game. But here we require that not only the player is playing the best response at the root, rather the player should be playing the best response at every state of the game. Right. This is what we mean by sequential rationality. And when analyzing extensive form games, it's very typical that we make this assumption, namely sequential rationality, that we expect the rational player to play in a way that are sequentially rational. So now, given this game, we want to give you a sort of intuitive idea of what we mean by a sequential rational strategy. So this requires a definition of a subgame. A subgame is a game defined on subtrees of the game tree. So basically, suppose we have a game tree, we consider a sort of a subtree that would be a tree that's starting from some node and extends to only those leaves that are below it. So it disregards the other nodes that are above it. So that subtree is defined in such a way that the subtree would consist of a node and all its descendants. And for every node in the subtree, if a node x prime belongs to the same information set, then that x prime also belongs to T, right? So we would need to have this condition because of the fact that there are nodes within the same information set. You cannot separate the node in an information set from another node in the same information set in the two different subgames, right? So if I define a subgame, basically you need to contain the entire information set, right? So if you have a perfect information game, this is a very simple picture. For every node, it defines a subgame because every node is just itself an information set, right? Which are illustrated by these dotted lines here. Notice that each subgame consists of a node and all the nodes that are below it, all the way to leaves. But if you have an imperfect information game, for example, this one, where you have these two nodes being in the same information set, then there is no subgame that are enclosing only this branch of the tree, because this node has to come along with this node, which belong to the same information set. Okay? So basically, the subgame will be starting from this node. And so it contains all of these nodes in the same information set. So now in this picture, we only have two subgames, one which is a whole tree and the other one which starts from this node. So that's the notion of subgames. And then we can define this notion of subgame perfect equilibrium, which is proposed by the famous economist Sultan, who won a Nobel Prize in the 90s. For any strategy profile S and a subgame, we use this notion S with a hook together with that subgame. That's basically denoting the restriction of the strategy to that subgame only. So this basically means that the players follow exactly the same strategy as S, but it's only on that subgame. Right, so we use this to denote the strategy profile restricted to nodes in that subgame. And a strategy profile S is a subgame perfect equilibrium if for every I and for every subgame, that restriction of the strategy to that subgame is a natural equilibrium in that subgame. Right. So this basically means that this is a much stronger notion than simply Nash equilibrium. Right. Nash equilibrium says we are playing this game when everybody is playing their best responses at the root. But a subgame perfect equilibrium is saying that we're playing this game when everybody is playing their best responses at every information set or at every subgame. Right. So that basically means that strategy profile will be a Nash equilibrium at every subgame. So if you consider now this case, well, for this case, we have a perfect information game. Then this means that with every non-terminal node, we will define a subgame. And at every non-terminal node, we will consider what's the best response of players. For example, at this node, which belongs to player 2, player 2 would choose the outcome that's most beneficial to himself, which is the left branch, right? Because the left branch would give him a 1 payoff instead of a 0 payoff. So clearly we'll adopt this branch. At this location, he will clearly adopt the right-hand side branch because 2 is bigger than 1. 2 is bigger than 0, right? And so that's the player 2's best response at the subgames. But if you look at the overall subgame, which belongs to player 1, he will look at, well, according to the definition of sequential rationality, according to the assumption that player 2 would be sequentially rational, we know that given this tree, we know that player 2 would go this way and also would go this way from here. Then player 1 will see that, okay, either I will get a payoff of 2 or I will get a payoff of 1. And which one is better? Well, actually, the left-hand side is better. So player 1 would choose capital O as the action. Right? You see the difference here is that every player now assume that the other player is a sequentially rational player, right? And this eliminates a lot of, well, potentially eliminates a number of possible actions of the opponents from consideration. And therefore, this game has only a unique subgame perfect equilibrium, namely capital O and small case o and f. Right? That's the only subgame perfect equilibrium in this game. In fact, Kuntz's theorem, which is also fundamental to game theory, says that every finite perfect information extensive form game has a pure strategy subgame perfect equilibrium. So we, for this case, it's okay just to consider the pure strategy equilibrium now. Right? We can find the SPE using an algorithm which is called backward induction. Right? And that procedure is almost exactly the same as how I described to solve this example, because where I have identified the subgames, and now I start to examine the behavior of the players from bottom up. I first of all go to the lowest level subgames and I make a decision on the action of the players, and then I go up, and when I go up, I assume that the opponent will follow the decision that I just analyzed. So in this way, iteratively, eventually I reach the root of the tree, and that will give me strategies for all the players, and they are deemed to be in SPE. So basically, we identify equilibria in the bottommost non-terminal nodes, and then iteratively we go up until we reach the root of the tree, which is described in this backward induction procedure. You can see that it's very, very intuitive, and in fact that we have seen this strategy before, right? In our undergraduate AI course, I assume that everyone who's taken the first course in AI has seen the minimax algorithm. Essentially, that's the backward induction algorithm for zero-sum games. Right. So now we have this example. We have this game, and we want to apply backward induction to find the SPE. We have so many strategies. If we want to find out Nash equilibrium, we need to draw this n by n table, and then we identify Nash equilibrium this way. But for efficiently finding the SPE in this game, we just need to analyze each subgame. So here, player 1 would choose G instead of H. And then here, player 2 would choose C instead of D. And now here, player 2 would choose, well, he would need to consider either should get 5 or get 10. So in this sense, of course, getting 10 is better. So player 2 would choose F. And then here, the player 1 would see whether he would get D, which is, whether he would get C, which is, sorry, this outcome, which is 3 for player 1, or he will get 2, right? So in this sense, of course, 3 is seen as more attractive than 2. So player 1 would choose A. So according to backward induction, we're going to have player 1 choosing A here, player 1 choosing G here, player 2 choose C here, and player 2 chooses F here. Right, so that's the unique SPE for this game. Like what I said, backward induction computes an SPE in linear time to the size of the game tree. So it's incredibly fast. And like what I said, it essentially is a minimax algorithm for zero-sum games. Because in zero-sum games, at each level, we're looking at alternating between the minimum reward and the maximum reward, and so on and so forth, right? And the minimum reward is actually maximizing the opponent's reward. Of course, one of the note is that even though this algorithm is very simple and it has a very fast complexity, it's still not useful, especially for practical games where we have a very large search space. And so the search space will correspond to the game tree, which correspond to, potentially billions of nodes. And even though we have a linear time running algorithm, we would not be able to derive the strategy. It's just too much. Well, not only billions of, there could be 10 to the power of 150 nodes. Huge number, and of course we are hopeless if we want to generate the entire game tree. So that finishes today's lecture, because we've mainly spent time introducing extensive form games, generalizing static games to dynamic cases, but we've demonstrated the relationship between static games and dynamic games, and we've introduced the aspect of information. So either we have perfect information, in which case everything is known and simple, or we have imperfect information case where the nodes are grouped as information sets, and decisions are made on the information sets instead of the nodes of the game tree. And we've introduced behavioral strategy, which is a new concept. So it's a different forms of random strategies. And we've looked at subgame perfect equilibrium as the outcome of sequential rationality. And then we look at backward induction algorithm, which is very simple and essentially should be familiar to most people. I think that finishes today's lecture, and I'll see you in the next lecture.